neural scaling laws.
Okay, great, thanks, man. And yeah, it's great to go after Greg actually because he set me up so nicely. Okay, so I just wanted to start with some philosophy or physics. Data is the dark matter of theory in deep learning. Like we can't hope to understand what deep learning is doing if we don't have an understanding of what we are asking deep learning to do. And what we're asking deep learning to do is fundamentally embedded in the data because that determines training loss and so forth. And so, just as in other domains, nothing in biology makes sense except in light of evolution. Nothing in neuroscience makes sense except in light of behavior. These are famous quotes by other people. I'd like to become famous someday, so I wanted to add something. This is my quote, not ChatGPT. Nothing in deep learning makes sense except in light of the structure of the data. It's not quite as pithy and probably won't be famous, but anyway, I still think it's true. Right? So now this is a problem, right? Because our lack of understanding of the data. Oh,
when you say in the light, you mean through the lens of?
Oh, sorry, the thing wasn't on. Okay. Our lack of understanding of the data is becoming a fundamental problem. For example, in some cases, we don't even know what the training data is, like in GPT-4. Yet we do see remarkable new capabilities, for example, solving exams. But I'm sure once you saw this, your immediate question that you asked was, well, to what extent are the problem questions on these exams already in the web? And these things trained on the entire web, right? So how surprised should we be by these new capabilities when the pre-training set is the entire internet of, say, text and code? And even in it, I don't think it's the case that it's just copying stuff. It's really combining things in really interesting ways to answer interesting questions. But even if we know what the pre-training data set is, how different really are the tasks that are performed at, say, test time, like in-context learning tasks? How different really are they from things that we're seeing during pre-training, right? We don't really have a good understanding of that. So we're going to ask kind of two questions, especially about the diversity of the pre-training set. For example, how diverse does the pre-training set need to be to enable new capabilities like in-context learning of new tasks? And how different can the new tasks be seen? How different can the new tasks be from the pre-training data, right? And also, neural scaling laws, we've seen several talks on that here. Performance scales with the amount of data, but does the quality of the data matter or the diversity of the data matter? And if we can create more diverse data, can we beat these neural scaling laws? So that'll be the second part. So basically, this talk is kind of two parts. The first part builds actually off of what Greg was talking about. So we're going to focus on in-context learning of regression, but the reason we do that is to really sort of try to address this question in a controlled setting, right? By focusing on regression, we can, one, define a space of tasks. Two, we can define a metric on the space of tasks that allows us to quantitatively assess how different a new task is from the set of pre-training tasks. We can parametrically vary the pre-training data or task diversity in a controlled manner. We can derive optimal Bayesian in-context learners under different priors. And we can quantitatively understand transformer performance in relation to these various Bayesian learners. So we can sort of really understand what's going on. And what we're going to find is we're going to find a phase transition in which in-context learning suddenly emerges at a threshold task diversity in the pre-training set. And this emergent capability cannot be explained by Bayesian learning with the pre-training task distributions of prior. So there have been various approaches to try to explain in-context learning as just Bayesian inference. But it turns out that's not the case. It's actually a failure of Bayesian inference here that leads to good in-context learning of new tasks. And then in the second part, we're going to show that the slow power law scaling of performance with respect to data set size indicates that data is actually highly redundant. And by finding non-redundant, more diverse data sets, we can significantly outperform these existing neural scaling laws. Okay, so let's get started. And so both of these works have been recently, at least on the archive or have been published. So the first is this paper, Pre-training Task Diversity and the Emergence of Non-Bayesian in-Context Learning for Regression. It's work done by three really talented grad students, Alan, Manshij, and Feng. Okay, so we're going to have the same setup that Greg talked about, so it'll look familiar, but the notation's of course all different. But we're going to do some twists on the distributions. Okay, so what is a single task for regression? We're defining a single task to be an unknown regression vector in d-dimensional space. You get k input-output pairs, so the x's are inputs, y's are outputs. The y could just be a scalar. We're going to draw a single unknown regression vector from an isotropic Gaussian in d-dimensional space. The input will also be isotropic Gaussian, and the output will be labeled by the true regression vector plus noise. So we're going to work in a noisy regression setting. And so this is just a d equals one-dimensional example. Now, how do we define the in-context learning problem for a transformer? We're going to do it the same way. We're going to do it autoregressively. So we're going to have a transformer here. We're going to feed in the context here as a sequence of input, output, drawn from some task. So there's some unknown regression vector W that relates the y's to the x's here. Okay. And now we're going to have a sequence of contexts. So for each context, say the kth context, it sees the first k minus 1 input-output pairs, and then it sees a new kth input, and it's got to get the right output for the kth input, based on the knowledge of the context of the previous k minus 1 input-output pairs. So for example, here's context k equals 2. You see input 1, output 1, input 2, and its task is to come up with a prediction for y2. It hasn't seen y2 yet. That'll appear in the next context. And so it's all done autoregressively. Okay. The loss function just squared loss on the outputs in sequence. Right? So, okay, so that, I mean, that's what we're going to do in context. But where do we get this transformer from? We pre-train it on a distribution of tasks, right? So this is the pre-training process. So here's where we start to make some departures. Here's where we parametrically control the task diversity in the pre-training data distribution. So imagine we have a pre-training data distribution where there's a fixed number of capital M unknown tasks, right? And they're drawn once and for all from an isotropic Gaussian, but then they're fixed. Okay? So this is our kind of limited task diversity, and M is the pre-training task diversity parameter. And the pre-training loss function that we're going to use to derive our transformer weights is just this loss function. Basically, we choose a W from a uniform distribution over these M discrete task vectors, right? And then we draw random inputs, random noise, and we, of course, get the labels. And then we minimize the squared loss for all different context lengths, right? So, okay, but then for actual pre-training, we estimate this expectation, as we usually do in machine learning. We construct a mini batch, okay, and we sample some number of examples this way, and we take a gradient descent step with respect to the loss function on that mini batch, and we iterate many, many times, right? So this whole pre-training process, it's going to see lots and lots of different inputs and outputs, right? But they're all going to be derived from a finite set of task vectors, right? So that's like a data set that's not very rich in terms of its content, right? But ideally, we'd like to do in-context learning of fundamentally new tasks that are different from any of the tasks that were seen during pre-training. Okay, so that's our goal. So then how do we assess that in-context learning? So now what we do is we have a new task vector drawn from just an isotropic Gaussian distribution. So it's like a sphere in high dimensions, right? And the loss on a completely new task is the same thing, except the distribution of pre-training tasks is replaced with the true distribution of our tasks, right? And so this loss function measures performance on fundamentally new tasks. Okay. All right. Now, what are some theoretical limits that are interesting to compare our transformer to? Okay. The one is the Bayesian approach, right? Which is just says like in prior theories of in-context learning, let's just consider a Bayesian learner that learns the distribution of tasks in the pre-training data, because that's all it ever has that's all the transformer ever has access to, the distribution of tasks in the pre-training data. Okay, we're going to assume, because we train the transformer for so long, we're going to assume that the transformer could, or we don't even have to make that assumption, but to motivate this algorithm, we can think of the transformer as implicitly learning the M finite regression vectors that were hidden in all the input-output examples that it got. And then if it were to know that, we could ask, what would an ideal Bayesian observer do, or Bayesian estimator do, if it knew the M pre-training task vectors, and it needed to predict the output to some new input? Well, what we could do is we could just compute the posterior mean of the output given the context and the m task vectors. And that's a very easy posterior mean to compute. If you compute it, it looks like you're effectively computing a regression. You're computing a regression estimate where the estimated regression vector is just a weighted average of the unknown of the regression vectors in your pre-training distribution, weighted by the likelihood that they were to make the prediction that was observed. Right. So roughly, it's like a Bayesian estimator that has memorized these m vectors, and it uses them in an optimal way in the minimum mean squared error sense to predict the output to any given sequence of contexts. If you have no data to begin with, then you just take the average of all of your regression vectors. So all of you could do this calculation in a few lines, right? Of course. So we call this the discrete minimum mean squared estimator because it's the MMSE estimator if you know the prior distribution over this discrete set of tasks.
So,
Yeah.
Just a question. So here, like if you only saw each task like once,
Yeah.
then
Yeah, we don't work in that setting. So that's another big difference from the way you guys do it. You see each one many, many times. I'll show you the numbers on the next slide, on a couple of slides when I show you. So basically, you have like m tasks.
Yeah. So you do many epochs over the.
Yeah. So when you construct a mini batch, you choose for each member of the mini batch, you choose one of the W's from the set of m W's, and you choose a fresh set of inputs and a fresh set of outputs.
Yeah.
So you're seeing many, many different inputs and outputs. There's no repetition there. That's like one epoch in inputs and outputs,
Sure.
but it's multi-epoch in the unknown regression vectors or tasks. It's like saying, I'm going to sample as many Wikipedia articles as I can, but they're always going to be Wikipedia articles and they're never going to be Shakespeare, right?
Yeah. No. I guess as this notion of the Bayes optimal sort of estimator, I guess here it does sort of make sense because the transformer could sort of understand the distribution with respect to what is optimal. Although if you sort of formulated it as like if there's a bit of uncertainty into like whether or not you actually ever do include one of these tasks, then it's sort of
We actually tried another theoretical approximation, which is the noisy discrete MMSE, where you get a noise, your prior is a noise ball around each of these tasks.
okay.
And that as you increase the noise, that interpolates between this and ridge, and it never quite explained what the transformer does. But interestingly, these two things that I'm about to show you explain what the transformer does in two different settings. We'll get into all of that soon. Okay. Now, the other option is just, what if you knew the true distribution of tasks to be an isotropic Gaussian, and then you have Gaussian noise and all that, then what's the MMSE estimator there, right? Well, we all know that that's ridge regression, where the ridge parameter is set by the noise of your outputs, right? Okay, so this is the ridge estimator, and this will do really, really well on new tasks. The DMMSE will do really, really well in the pre-training task distribution, but it will not do well on new tasks. Okay, so now the natural question is, well, what does the transformer do? And how does what it learns depend on the task diversity parameter M, the pre-training task diversity parameter M? Okay, just one more measure of what the transformer is doing. We can also compute the distance in prediction space between the function learned by the transformer and these two interesting functions, right? A ridge or DMMSE. And so there we just take the output of the transformer, the squared difference between the prediction of, say, either ridge or DMMC, whichever one you're using at the moment, and we average it over the true task distribution, right? And of course, a random distribution of inputs and outputs. And so this just tells you how far is the function learned by the transformer from either ridge or DMMSE, and we'll plot that in future figures as well. Okay, so now let's look at our first result. So there's a bunch of things to unpack here, okay? So on this horizontal axis is the pre-training task diversity, right? This is the parameter M. It ranges from 2 to 2 to the 20th or so, okay? The vertical axis is the error on the final example. So I could show you these autoregressive curves that Greg was showing you, but I'm just showing you the final error as an example. The final error is non-trivial because there's noise, so it can be non-zero. Okay, so let's just look at the performance of DMMSE and Ridge. So DMMSE is the green one, right? So if you are evaluating the error on the pre-training task distribution, then DMMSE is the best you can do. So the green curve is always the lowest. And of course, the absolute error rises as you get more and more tasks, right? Because, the Ridge does worse on the pre-training task distribution relative to DMMSE because the DMMSE knows the exact M task vectors that were in the pre-training distribution. Ridge doesn't. It just knows an isotropic prior. Right? So Ridge will do worse. Of course, as the number of pre-training task distributions becomes really, really large, DMMSE and Ridge should approach each other. Okay, that's what's expected. What does the transformer do? That's this orange line. It behaves exactly like DMMSE at low task diversity, right? So it's as if the transformer is somehow memorizing the limited diversity in the pre-training set. But after the amount of pre-training diversity grows beyond a certain threshold, it no longer can do that. And then eventually it snaps into what Ridge can do, despite the fact that there isn't that much task diversity at the point where the transformer snaps into Ridge, right? So interestingly, the transformer is failing to minimize its pre-training loss, but when it fails in an interesting way. It becomes Ridge, and it'll do well on new tasks. Okay. Now let's evaluate. So this was all evaluating performance on the pre-training task distribution. Let's look at the same performance on the true task distribution. So this is like how well does each algorithm solve new tasks that are not in the pre-training data set. So Ridge now is the best thing you can possibly do, right? So Ridge does really, really well. Okay. DMMSE does really poorly, right, at low task diversity, and then eventually it'll approach Ridge. And then here's the same snap-in behavior of the transformer. It behaves like DMMSE on new tasks, so it cannot solve new tasks well. And then eventually it snaps into Ridge, and now it can solve new tasks well. Okay. Just some numbers. It's a GPT-2 architecture. The input dimension was 8. We had a batch size of 256 and 500K training steps. So that's like 128 million examples. So you're seeing these however many tasks many times because we're taking 128 million gradient steps, or we're seeing 128 million task examples. Okay, now a natural question is, well, what if we were to train for longer? Oh, sorry, go ahead.
Does the size of the transformer affect how long it'll continue to behave? Like,
yeah, we'll talk about that in a future slide. Yeah.
Is there any relation with like pseudorandom generators, right? If I have a subspace of items, but it's kind of hard to distinguish it from a larger subspace of more uniform.
We could play with that with more interesting distributions over true regression vectors W. We haven't tried that idea yet.
Is the red curve, can you think of it as the Bayes optimal estimator for the distribution where you have this set of tasks, but each task, you never see examples from it with some tiny probability, 0.001.
We haven't tried that. What we did try was you get a noisy estimate of each task, right? And that's like the smooth discrete MMSE. And that algorithm's learning curve, even if you optimize the noise, doesn't match this orange curve. So we can't approximate what the transformer is doing, at least in terms of performance, with that heuristic estimator.
Sure. Because what would this distribution basically says, look, like if the likelihood of this having come from one of your tasks is too large, then you need to then just do regression, otherwise snap it to one of these tasks.
Yeah, exactly. Yeah.
That seems so. Might be similar.
At low task diversity, it kind of explains what's going on in the transformer. So at least for this small number of tasks, the transformer can acts as if it knows what each of the tasks are.
Yeah.
My question is related to this slide. So it's like it sounds to me if you train for sufficiently number of steps, the transformer should fit the creators. If you keep training.
Okay, that's a good question. That's exactly what we're going to ask next.
So there's a region like
It turned out not to be true.
the shift from the green to the yellow, the blue dots. It seems like you are doing early stopping, so you get a ridge-like behavior. I'm not sure if that's the right understanding.
We're not doing early stuff.
But I mean, the number of training steps is fixed, but the number of tasks.
So we're
are
gonna
increasing.
exactly. So we're gonna vary that, right? Let me show you what happens when we vary that, and if that doesn't answer your question, we can come back to it. Okay, so that's where these red arrows are coming in, right? So we trained for 500K steps, right? What would happen if we trained for longer, right? What would happen? Of course, DMMSE and Ridge won't change. There's no training involved in those. What will happen to the transformer? It turns out that the performance will become more like Ridge if the task diversity is high, and become more like DMMSE if the task diversity is low, which means that this transition will become sharper if we train for longer. So let me show you the evidence for that. So what are different ways that we could train for longer, right? We could keep all the hyperparameters of training the same, but increase the batch size. So here the batch size was 256. So we increased it to 512 and then to 1024, right? And what we found, so this blue is the smallest batch size. That's what you've seen before. Oh, and this axis is the distance from the pre-trained transformer to Ridge in the prediction space. So it's just a measure of how close is the pre-trained transformer to Ridge as a function, right? So you see that over here, if you train for longer or train with more data at the same fixed task diversity, then what happens is at a threshold task diversity, if you're up here at high task diversity, you actually become more and more like Ridge, right? Even though you're training with more data and a fixed number of tasks, you don't get closer to DMMSE, you get closer to Ridge. However, at low task diversity, if you increase the amount of data, you get further away from Ridge, and it turns out that you get closer to DMMSE, right? Okay. Another way that you could increase the amount of training is just keep the batch size the same, but increase the number of training steps, right? Let's say we go from 500,000 training steps to 1 million training steps. You get a similar pattern at a similar threshold, right? Again, so at high task diversity, more training makes the PT more like Ridge that would do well in new tasks. But at low task diversity, the pre-trained transformer PT becomes less like Ridge on new tasks. Okay. So this is what we use to define a task diversity threshold. It's the threshold that demarcates these two phases, where if I train more, I become more like Ridge. That's this phase. And here, if I train more, I become less like Ridge. So here's this kind of this phase transition, right? So this horizontal axis is the task diversity. Here's this task diversity threshold. Here I become more like Ridge if I train longer, and here I become less like Ridge if I train longer. So there is this algorithmic phase transition in the pre-trained transformer at this task diversity threshold, where it transitions from being more like DMMSE to more like Ridge if you train longer. That's the definition of the transition. Okay, here's a direct demonstration of the emergence of in-context learning for new tasks. So let's say I start with my pre-training distribution, and I have a finite set of tasks. So this is the d-dimensional input space. These are the m vectors corresponding to the m true regression vectors. I could track the performance of all three algorithms if I interpolate between two pre-training task vectors, right? So I generate new problem instances where I interpolate the regression vector between two regression vectors that are in the pre-training distribution. So new tasks will be in the middle. Alpha is an interpolation parameter. And you see that at low pre-training task diversity, so here's the orange is the pre-trained transformer, it does really well on the two tasks that it had already seen, but it does terribly on new tasks that it hadn't seen before. But Ridge, of course, always does well, but it does worse than DMMSE and the pre-trained the pre-trained transformer on tasks that they had both seen before, right? Okay, as you increase the task diversity here, you suddenly see the pre-trained transformer switches from DMMSE to Ridge, also in this kind of context. And then you see that it behaves like Ridge. So now Ridge does well on new tasks, and DMMSE doesn't do as well on new tasks, right? So, so that's kind of a direct kind of visualization of how this thing can learn new tasks beyond the task diversity threshold. Okay, so now how does the task diversity threshold scale with the input dimension, right? So the volume of tasks is exponential in the input or task dimension, right? The way to think about that is an isotropic Gaussian in high dimensional spaces concentrates in a sphere. The surface area of that sphere is exponential in the dimension, right? So, for DMMSE to really sample all of this space, it would need exponentially many task vectors, right? But then how does the task diversity threshold scale with D, right? Does the PT also need to see exponentially many tasks in pre-training to solve any new task well? And it turns out it doesn't, surprisingly. So here we scaled the number of dimensions, scaling the signal to noise ratio of the problem so it's always constant. And so we did the same experiment where we increased the batch size and we asked you to become more like Ridge or less like Ridge. And that transition determines the task diversity threshold. And you can see that when you go from 8 to 16 to 32 dimensions, you go from a task diversity threshold just above 2 to the 14th to 2 to the 16th to just above 2 to the 16th. So roughly the scaling, it's hard to do these training runs as you increase the dimensions. But roughly, at least for this limited range, we see that the scaling of task diversity with task diversity threshold with dimension appears favorable. It seems to be linear, right, in this setting. We could ask the same thing about what about DMMSE? Well, we can't scale the number of tasks exponentially with dimensions. We asked a slightly different question. For the largest number of tasks that we looked at, 2 to the 20 tasks, right, we computed the distance between DMMSE and Ridge, right, as a function of the dimension. And you see as the dimension gets larger, DMMSE gets further and further from Ridge. As you'd expect, right? You have a finite set of tasks, but you're increasing the volume of the sphere. So DMMSE doesn't behave like Ridge. It gets worse and worse as the dimension increases. But in this range of dimensions, the pre-trained transformer has no such growth of distance to Ridge. It really behaves like Ridge. Partially because the task diversity threshold is somewhere around here. So the scaling of the pre-trained transformer performance with dimension is vastly superior to what a Bayesian in-context learner would do in this setting. So again, the emergence of in-context learning cannot be explained by Bayesian theory with respect to the pre-training task distribution here. Yeah.
I have an intuition that, the threshold should depend on the capacity of this.
We're going to get to that.
Because you want to memorize the discrete cycle lengths by transformers.
There we go. Title of the next slide. Yeah. Yeah, good question. So
I still claim that this is Bayes optimal for prior, which is indistinguishable from, with respect to your prior, it's not Bayes optimal. But there's a prior with respect to which it is optimal, and you can't distinguish the two priors from each other.
I disagree. Maybe we can talk about that later. It's not Bayes optimal with respect to the true prior. Ridge is Bayes optimal to the true prior.
No. But with respect to the distribution on which it's like there is a prior with respect to what it's that's consistent with the example.
Yeah, but that prior, if it exists, has not been written down yet in this talk. Right? I don't know what that prior is.
Oh, it's just where there are some of these true tasks, where there's some zero, where you don't actually see it in any of your batches.
That's extremely unlikely in our setting, right? Like
no, it doesn't. In your setting, but you can't. If you adjust this model, you see some finite number of tasks.
Yeah.
But this prior that there might be some tasks where I see them 0 times or I see them 1,000,000 times. There's a small probability I see them 0 times. That is a valid prior. that's consistent with
Yeah, but
everything.
you still have to prove that it explains the pre-trained transformer behavior, right?
That's true, but probably not. Like, no, I mean,
I would say it's almost, my intuitions are completely opposite. I would say it's, by large deviation theory, almost extremely unlikely to, because we're showing 128 million examples and we have like, 2 to the 10 tasks, right? So it's extremely unlikely to never see examples from one task. Extremely unlikely. So how could, if an event that's unlikely to happen in the pre-training process, but is likely to happen in your prior, how could it explain what's going on?
Yeah, I'll take off.
Let's talk afterwards, yeah. Yeah. Yeah, it's growing. Like if you increase the batch size by 2, the total amount of training data grows by 2, basically.
And what makes the transition sharper?
You just train for longer.
So amount of training data. So the way it's being scaled is like M is total amount of data is also
M is held fixed, right? So in these plots, so the easiest one to think about is the pre-training data, right? The horizontal axis is the task diversity. That's M, right? So that's held fixed. In fact, everything is held fixed, except I'm just increasing the batch size, which means I'm seeing more examples per task. And then I ask, do I become more like Ridge or less like Ridge? And here I become more like Ridge, and here I become less like Ridge.
Do you have intuition in terms of if I fix the total amount of data that I want to see, like if I want to kind of think about maybe like a more practical setting, I might have a fixed amount of data. I increase M, but then the number of examples per task is decreasing. How does that?
Yeah, I don't think we've done that specific experiment. But you can see variations in M by walking along these curves, right? So this is, I guess this is this is increasing M and decreasing number of examples per M. That's what these curves are doing.
Have you tried to verify concept prior?
Oh, no, we haven't. We have tried a Laplace prior. And then at high task diversity, the pre-trained transformer behaves Bayesian with respect to the Laplace prior over the whole space. And at low task diversity, it behaves like DMMC again. So you get the same behavior, right? So, except it generalizes the Laplace prior. So these pre-trained transformers are really good. What's surprising here is that they're really good. Well, let me summarize the surprise later, or emphasize it later. Okay, the capacity question. So it turns out, like for example, with regularization, what these plots are telling you is increased weight decay reduces the task diversity threshold. So weight decay is somehow regularizing, is of course tautologically regularizing the training. And what that, intuitively, you might think that prevents the pre-trained transformer from memorizing the limited number of tasks. And therefore, at a lower task diversity threshold, it'll start to be able to solve new tasks better. And that's what happens. Increasing the model capacity does not appreciably change the task diversity threshold, but we're already starting from a pretty large model, right? It turns out if you reduce the model capacity, it increases the task diversity threshold. Decreases the task diversity threshold. Oh, sorry, weight decay means you just add a W squared term to your loss. So the gradient is minus W, so you're decaying all the weights. Okay, so now where might this algorithmic phase transition be coming from? What might be a mechanistic explanation for it? Short answer is we don't know, but I can give you our current best guess. Okay, we can try to peek under the hood and look at the pre-training learning dynamics, right? We've never looked at that yet, right? So this axis is the number of pre-training steps, right? Up to 500K pre-training steps. These different colors are different pre-training task diversities, right? So blue is low task diversity, pink is high task diversity, and so forth, right? This is the distance between the so these are not error learning curves, but they're distance learning curves. The distance from the pre-trained transformer to ridge in function space or prediction space, evaluated on a random distribution of tasks drawn from the true distribution of tasks. So this is measuring how close are you to ridge on just a isotropic Gaussian distribution of tasks, so the most general setting possible. Okay, and what happens at low task diversity is initially the pre-trained transformer becomes closer to ridge, but then it runs away and becomes further away from ridge. And when it does, it becomes closer to DMMSE, it turns out. The same effect happens at a slightly higher task diversity. If you lower the task diversity, if you increase the task diversity even more, you get this sudden transition where the curves are monotonically decreasing now, right? So now what's happening is they don't see the DMMSE solution. They just keep getting closer and closer to ridge. They don't get trapped by the DMMSE solution. You might ask, well, what if I train for longer, right? So this is what happens if I 4x the number of training steps. I go from 500K to 2 million. And this dichotomy between the two types of learning curves is largely preserved around the same task diversity threshold. And that's the same threshold that we've roughly been talking about.
2 to the 10 tasks.
Yeah, that changes
That
slightly.
changes.
That
So
changes
if you keep
slightly.
training more, I would say like the even more task diversity you still get away from. But you need
turns
to
out
train very, very well.
potentially, but I think it's very unlikely. I think this green curve is right at the border, so it's quite sensitive. And the purple curve is much more stable. If you train for longer, it still won't eventually go up. And I'll give you more evidence for why right now. Okay. So here's part of the evidence. You could ask, how does the training time scale with the task complexity? Okay. So we could just have a convenient measure of this, what might be considered an optimal early stopping time when you're closest to ridge. But by the way, even when you get closest to ridge, you're not as good as ridge. So you can't use the optimal early stopping time to get a good pre-trained transformer that can do in-context learning of new tasks by just doing early stopping. Okay? But in any case, we can compute this turning time, we'll call it T star, and ask how does it scale with M? It turns out it scales as a power law with M, approximately with a square root scaling, right? Until you get to this task diversity threshold phase transition, where suddenly it jumps up. By definition, jumps up to, it's a 500K here because it never turns around, right? So now, if you were to suddenly increase the training time, if this were not a stable picture, what would have to happen is suddenly this thing would have to drop down all the way to here in order to match this square root of scaling, or some of the scaling law changes, which both scenarios seem pretty unlikely, right? And we've done other experiments. We've done many experiments now where we increase the training time and we don't see a huge difference in the task diversity threshold. Okay, so now here's kind of the take-home message, right? So as you increase the task diversity M, it takes longer and longer for the pre-trained transformer to stop moving towards ridge and eventually turn around to DMMC until beyond the task diversity threshold, it never finds DMMC. Okay. But here's the thing. So DMMSE is the thing that minimizes the pre-training loss. That's what we're used to doing. Like we want to figure out what minimizes the pre-training loss. Now, when something doesn't minimize the pre-training loss, there could be infinitely many ways it could potentially underfit. So there's many ways to fail, right? It's like all failed machine learning models are different in different ways. The happy ones are all the same, right? So, so when the pre-trained transformer fails to minimize its pre-training loss by failing to find DMMSE, it in some sense, interestingly enough, fails in the best possible way. It finds ridge, which is quite surprising. And it's precisely this failure of pre-training that allows the emergence of in-context learning of new tasks, because ridge is fundamentally the algorithm that can do new tasks. Yeah.
Does it fail to minimize the training loss?
Yeah, it does.
I mean,
That's what you see. Well, at least relative to DMMSE.
DMMC?
So that's what we showed in the beginning, right? The error of the, at high task diversity, the error of the pre-trained transformer is higher than the error of DMMSE. So I'm going to give you a picture that I think that's at least consistent with the data so far on the next slide. Okay. So this is an important clue, right? When it fails to find DMMSE, it finds ridge. And there's a sudden transition between the two. So what might be the case? So whenever there's a failure of machine learning to find the best possible solution to the pre-training loss, which in this particular case is DMMSE, there's two potential reasons for the failure. One is an expressivity problem, right? There might be no configuration of transformer weights that can realize DMMSE. That might be true. Another possibility is it might be a training failure. There may be such a configuration, but its basin of attraction is so small that SGD cannot find it, right? Let's say it were the second possibility. What might this phase transition look like in terms of a loss landscape? This is our current best guess for it. So at low pre-training task diversity, this is the pre-training loss as a function of the transformer parameters, a cartoon, right? There's a DMMSE point and a ridge point. And there's a global minimum at ridge that's wide enough that SGD can find it. Okay. And that's what we see. At low task diversity, the transformer behaves like ridge. Okay. At high task diversity, assuming that DMMSE is part of the set of expressible functions by the transformer, there must be a minimum of the pre-training loss at DMMSE, but it might be so sharp or have a basin of attraction that's so small that SGD cannot find it. And interestingly, there must be a second basin that's wide enough, that's found all the time, that has a minimum located at ridge, but its error is higher than that of DMMSE. And you can imagine, just like in physics, there could be a first order phase transition where this thing, as you increase the task diversity, this thing gets wider and develops a minimum. So it kind of falls, and this thing becomes sharper and sharper. That's my best guess as to what happens. You can already imagine that this kind of conceptual theory suggests various experiments to do to further test this hypothesis. Right? But this is what I think is happening in this phase transition. So let's see what time are we at. Okay, so that's my last slide for the first part. Are there any questions?
Actually, I think there is a third case. So if you take the task diversity to infinity, the DMMSE should recover region.
Yeah, that's right. But that happens at really, really large M.
Yeah. So there should be a third.
That happens beyond the M that we're considering at the moment.
Like suddenly the barrier, separate DMMSE, and that barrier should disappear.
Oh yeah, that's a good point. That's a really good point. At really, really large M, there should be one minimum that's located where DMMSE and ridge are. You're absolutely right. But if you look at like the regimes that we're looking at here, there's still a gap. There's still a gap between DMMSE and ridge. It's a small gap, but there's a gap nonetheless. But you're absolutely right. Like at really, really large task diversity, like everything's simple. But what's really interesting is that at really low task diversity, where there's a huge gap between DMMSE and ridge, the pre-trained transformer still prefers ridge. That's a surprising thing. It can't find the DMMSE solution. It finds ridge, even when ridge and DMMSE are really far apart. And that's what I was trying to capture in this figure here. DMMSE and ridge are far apart, but somehow the transformer likes ridge. Again, this is all speculation. This picture is all speculation, but it really is my best guess as to what's going on. And if we were to continue working on this, this would guide the experiments that we do, this picture.
Yeah, so some of your curves there look memoryless, and I'm a little curious as to whether or not
They look,
whether or not it's not this one. I'm not referencing this one.
Oh.
Some of your curves looked either geometric or exponential.
Oh.
And so I'm trying to figure out the characteristic of it, like, is it geometric or is it exponential?
I don't know. Yeah, I'm not sure. Okay. Okay, I wanted to talk about another setting. I think I can go through the highlights of this quickly. We started late, right? Like 10 minutes late, so
10 after.
10 after. Okay, perfect. Yeah, so about 15 minutes. Okay. So here's another setting where data diversity matters. It can actually change the scaling laws that we observe in practice. Right? So this is work done again by a very talented team. There's kind of a body of 3 papers here. I'm going to focus mostly on this paper, but this paper motivates this paper. Okay. So here's the basic idea. So some other talks in this workshop, we've looked at neural scaling laws. So that's where error tends to fall off as a power law with either the number of parameters, the number of data points, or the amount of compute. But the exponent's often pretty small, right? So I personally think advancing AI through scaling alone is quite expensive. It's definitely expensive. And there's a question as to whether or not it's sustainable, right? Okay, so for example, if you do language modeling with large transformers, a drop in cross entropy from 3.4 nats to 2.8 nats requires sort of 10x more training data, right? The scaling exponent is minus 0.09. So it's quite close to zero. Right? In large vision transformers, a similar thing. If you go from 1 billion data points to 2 billion data points, you can get a 2% to 3% improvement in image net performance, right? So you're kind of adding 1 billion data points and getting a 2 percentage point improvement. Okay, so this is what I mean by slow and unsustainable. Right? Okay, so let me give you the key ideas and take-home messages of the second part. So the key idea is that slow power law scaling of error with respect to data set size likely indicates that training examples are highly redundant, right? Almost tautologically, adding more examples doesn't help you very much. So they're somehow redundant. Okay? Therefore, we should be able to prune data sets to identify sparse subsets of non-redundant examples. Because they're non-redundant, they're more diverse in some sense. And if we plot error as a function of the size of a pruned non-redundant data set, then we might be able to beat this power law scaling. Okay, so what we do is we show analytically that we can do this for the perceptron learning in a student-teacher setting. And there, at least, we can achieve exponential scaling, both in theory and practice. Okay? And then in practice, in other settings beyond the perceptron, for example, ResNets trained on benchmark tasks, and vision transformers trained on pre-trained image and fine-tuned, we show how to beat power law scaling using these similar algorithms. We'll find that the way that we prune the data matters. So we perform a benchmarking study of many different pruning metrics. We develop a new metric that's cheap and scalable. It doesn't even require labels to compute, so you can use it on unlabeled data. And then we can sort of prune to 75% of ImageNet without suffering any drop in accuracy. And then in later work, we showed how to apply this to language models and much larger internet scale data sets in this paper. Okay. So how do we do this? So what's an interesting strategy to prune a data set? Right? Well, here's a simple heuristic that we explored in this paper with Manshij and Carolina. What we did was we trained on a data set, in this case CFAR10, for a very short period of time, right? And then for each individual example, we compute its distance to the decision boundary, right? And those that are far from the decision boundary on the correct side are in some sense easy examples. They can be learned quickly and correctly in a short amount of training time. Those that are close to the decision boundary, or even worse, on the opposite side of the decision boundary and far away, these are the hard examples. They're not confidently learned or either incorrect after a short period of training time, right? So we can rank examples by their difficulty, defined this way. Okay, we can do this a few times to average the scores, right? And what we can do is we can prune the data by retaining only a fraction f of the hardest examples. Okay. So then the question is, how many examples can you prune before suffering any loss whatsoever? And it turns out in CFAR10, we can prune about 50% of the examples. We can throw away half the data set. And if you train on that half data set, you do as well as if you train on the entire data set. And on CFAR100, we could throw away about 25% of the data set. Okay, so this is a reasonable heuristic pruning algorithm, but it raises a bunch of questions. Why does data pruning in this fashion even work? Why is keeping the hardest, quote unquote, hardest examples the right approach, or is it? Can we develop a mathematical theory of data pruning? And how does performance scale with pruned data set size? And more of a, can we scale it up? Would it work on ImageNet? Or do we need new ways of pruning for ImageNet? Okay, so to fix our ideas, we started from some theory, actually. So we just asked in the simplest possible setting, can we analytically derive the test error after pruning? Okay. So we started with the perceptron. So basically the model of the data distribution is as follows. We pick PIID random Gaussian inputs. We pick a random teacher perceptron with weight vector t. So here's your teacher. It has a decision boundary perpendicular to the weight vector. And we label the examples just by the sign of the dot product of the teacher with each example. So these examples are the plus examples, and these examples are the minus examples. So a two-way classification problem. So that's our model for the training data. Okay. The data pruning strategy, well, what we're going to do is we're just going to follow what we did in the deep learning and a data type paper. We're going to train a probe student for a short period of time, right? So that probe student will acquire some non-zero dot product with a teacher. Okay, and then we're going to compute the decision boundary of the probe student and compute the margin of each example with respect to the probe student. Remember, we don't have to have direct access to the teacher. We only have access to the training data. So we're going to compute the margins of the training data with respect to the decision boundary of the probe student. Okay, then we're going to keep the hardest data with the smallest margins with respect to this decision boundary, right? So we might keep, for example, this example and this example. Right? Then we're going to just throw away the probe and just start training from scratch, right? Just like we did before. And then we're going to analytically compute the test error of a max margin learner on the non-Gaussian pruned data. Okay, that's the strategy. We're going to work in the high dimensional statistics limit where the dimensionality of the problem goes to infinity. The number of examples before you start pruning goes to infinity, right? So the density, the ratio of the number of examples to dimensions, the data density, we're going to call alpha total. That's going to remain order 1. Right? And then f is an important parameter, the fraction f of examples that we keep. And so the size of the pruned data set is by definition f times alpha total. Okay? So that's our size of the pruned data set. And we're going to care about how performance scale or test error scales as a function of alpha prune. Okay, so the important parameters of the problem are theta, the angle between the teacher and the probe, the projection of the data onto the probe, the margin in this ratio. Now, there are certain quantities which concentrate in this high dimensional statistical limit and don't depend on the detailed realization of the training data and so forth. One is the cosine angle between the student and the probe. So the student is the perceptron that we train to completion after we do the pruning. That's going to have some angle with the probe, we'll call that rho, and it'll have some angle with the teacher, we'll call that r. And the test error is just the inverse cosine angle of the student with the teacher. So if the student is close to the teacher, the test error of the student is small. Okay. All right. We can write down, we can use ideas from the statistical mechanics of disordered systems, notably the replica method, to compute self-consistent equations for these quantities that concentrate, right? These happen to be the equations. From these equations, we can extract the test error. Okay? You don't need to worry too much about the equations. I'll tell you what their consequences. Okay. So here's an example of a result. So when so this is an example of when the probe equals the teacher. So theta is 0, right? So we have, in some sense, the best possible pruning metric. We're pruning according to the decision boundary of the teacher, right? This horizontal axis is alpha prune. It's the amount of data we have after pruning. Okay? This vertical axis is the test error, right? These different curves, or corresponding to different colors, correspond to different fractions of data kept, starting from different alpha total, right? So for example, if you keep 100% of the data, that's like doing no pruning at all. And you get a power law scaling of test error with data set size. And that's well known from classic perceptron theory. Right? Okay, but now what happens if you plot performance as a function of alpha prune for different levels of alpha total and f, right? So remember the relationship there's this relation between alpha prune f and alpha total. So there's many ways to get a particular prune data set size. I could start with lots and lots of data, large alpha total, and small f, or I could start with less data, like some smaller alpha total, and a larger f. So that's why at any given alpha prune, there's multiple curves. Right? Each curve eventually settles into a power law, so that corresponds to a fixed pruning ratio f. Right? But the Pareto envelope of this family of curves falls off as an exponential. And the way you trace this Pareto envelope is you start with larger and larger data sets and do more aggressive pruning. Right? So, yeah.
So you're just saying, suppose you sample a bunch of points, conditional on them being within distance, like alpha of a hyperplane.
Yeah.
What's the max margin?
What's a tester of the max margin classifier with respect to that data distribution?
As a function of the alpha,
The fraction of examples that I keep, yeah.
getting narrower and narrower.
Yeah, exactly. Yeah. And by the way, like over here, you actually do worse than no pruning at all. So that's an interesting observation. But in any case, there is a way that you can bend the scaling law from a power law down to an exponential here. And that's by doing, starting with larger and larger data sets and doing more and more aggressive pruning, right? And then you'll trace off this Pareto optimal frontier. Okay, so this is going back to this worst case. So here's an example. It turns out that if you have not very much data to begin with, right? That's when you have small amounts of data, like small alpha prune. It turns out it's not a good idea to keep the hardest examples. It turns out it's a better idea to keep the easy examples. And so here's the discrepancy between the two strategies of keep hard examples and easy examples. And if you have lots of data to begin with, keeping the hard examples is the better strategy. And if you have very little data to begin with, keeping the easy examples is the better strategy for the perceptron. But this makes an interesting prediction, right? Would this same prediction hold for deep neural networks trained on benchmark data sets? And remarkably, it does, right? I think this is the art of doing theory, is you work something out for a simple model, and that makes a prediction that hopefully holds far beyond the regime of validity of your simple model, right? So it turns out in ResNet 18 on CFAR 10, the exact same, this prediction actually holds. Nobody ever looked at, nobody meaning we, never looked at keeping the hard examples because we're always starting with lots of examples to begin with. But if you artificially reduce your data set and then prune after that, it turns out it is indeed a better strategy. So this, remarkably, the prediction from perceptron holds in a much more general setting. Okay, so again, here's the cartoon picture. When you don't have much data to begin with, keep examples of large margins, keep stuff near the poles. If you have lots of data to begin with, keep stuff near the equator, where T is the true regression vector. Oh, sorry, T is the perceptron. Okay, so
wait, if you don't have much data, then why not keep all of it?
well, we're trying to understand scaling of performance with respect to optimal data sets of a given size, right? And so, and these are non-Gaussian data sets. So how do you get that? So we're always looking at performance with respect to the pruned data set size. Right? Okay. So you do get an efficiency gain of training on the smaller data set because you don't have to train for as long. Here's just an advertisement about another paper where you can analytically compute the tester for non-Gaussian data and actually find the optimal loss and regularizer, but I won't go into that. Okay, there's interesting changes that happen when the probe has a different angle. But let's see, what can I tell you in like 2 minutes that's super fun? Okay, so just in practice, right? So we tried this pruning procedure for different problems, and we could see that we could definitely beat these black scaling laws, right? We can't quite get to exponential, but you can, and that's what would be predicted if we had an imperfect pruning metric, it turns out. But you can definitely beat the scaling law quite significantly if you prune the data in a certain way, right? It also works for vision transformers as well. Okay. So let me just tell you the fun stuff. So we scaled it up to ImageNet. There's an interesting algorithm that we came up with that doesn't even require labels. And when we use that algorithm, we can ask, you start to get some intuition for like, what are the easy examples? Why are they redundant? What are the hard examples? And why is it beneficial to keep them if you have a lot of examples to begin with? So this is our new pruning algorithm that works well in ImageNet. We can throw away 25% of ImageNet without any decrement in performance. And this is just a random class 100, happens to be Black Swan. These are the easiest examples, right? The ones that are learned quickly. And you can see that they're also quite redundant with each other. They're kind of canonical poses of black swans. Right? The hard examples are all idiosyncratic and idiosyncratic in their own way. So if you want to do well in ImageNet, you can throw away a lot of these, but you got to keep these. Another example is another random class 200, right? Tibetan Terrier. These are the easy examples. They're all kind of canonical and redundant. These are the hard examples. They're all kind of idiosyncratic, right? Including weird color maps here. And then the fun one, the tiger beetle. Again, the easy examples are here. Here's a hard example, which is a cartoon of a tiger beetle, right? Like this just all gets algorithmically picked out. So this is a great way to like kind of explore your data set. Yeah.
Isn't it because the easy prototypes just have more of what we're looking for in them compared to like hard?
Potentially. I mean, I would also say they're quite similar to each other.
Well,
Yeah.
because there's more of them. Like if you look at the beetle, there's just more beetle in the picture. Therefore, they're more similar.
Oh, more. Yeah,
because there's
yeah,
more beetle.
yeah. The reason I say they're more similar is that the algorithm we used for getting this was to put all of these images into the embedding space of a foundation model, cluster them into clusters, and take the examples that are furthest from the cluster centroids. So all of these images are closest to their respective cluster centroid. So they're all quite similar to each other as measured by Euclidean distance in the embedding space of a foundation model. Sure, when they're all more similar to each other, they have more beetle in them. But I think it's a similarity that's more important than, yeah. I mean, the similarity is what allowed us to pick these off. Yeah. Okay. We have no mathematical notion of more beetle that would ever play into their selection of these things. Okay, just again, we also figured out a way to this lion data set, 440 million images. We could scale it down, we could prune it down to half its size, so 220 million, without suffering any loss in performance, and then you train twice as fast. So when you start to be able to train foundation models twice as fast, you start to save, of course, time and money. We can also get like 15% efficiency gains on language models. Anyway, those details are here, and I'll just stop right there. Here's the summary.
Let's just take those questions.
Thank you. So when you prune your data based on like the probe state that's fairly early on in training, will that like bias your like ultimate training results to like look more like the probe state? And have you considered that in terms of like the efficiency gain of model training by doing data pruning in this way?
Yeah. So I do have that slide. Yeah, this is kind of the philosophy behind how model data pruning can be useful. But we looked for biases in the ImageNet classifier trained on the pruned data set. So we looked at does it do worse in certain classes than others? And if you don't class balance, it does, right? But if you class balance, you get rid of that, right? Now, in the situation where we train the lion data set, where we don't have labels, and we do have captions, but we ignored the captions when we did the pruning. And then we looked at the ImageNet classifier, we didn't see biases, right? When we trained a clip model on lion, we did a linear readout to train an ImageNet classifier on top of the lion embedding space. And we looked at the biases of that ImageNet classifier, and we didn't see any biases by pruning on clip. Right? So I think it depends. If you're pruning on the same data distribution that you're training on, you might have to worry about biases. But if you're not, you don't, at least in these limited set of experiments. I don't know if that made any sense.
Thank you. I think you mentioned this briefly. We talked about the Pareto envelope, and sorry if I missed more of it, but don't those curves also allow you to infer like optimal curriculum depending on data set size?
Potentially, yeah. We were kind of looking at just a one-shot pruning strategy, right? You could imagine all sorts of modifications where you train a little bit, you prune, you train a little bit, you prune, and so forth. You could even imagine sequencing the data points according to their difficulty. We didn't explore any of that stuff. The one-shot pruning is nice because it leads to this notion of a foundation data set, right? Like you have this huge lion data set that a bunch of people are training on. If you can find one subset that's just as good as the entire data set, we can just hand that out as a foundation data set and everybody can train on that instead, right? It doesn't require people to optimize the hyperparameters of curriculum learning or active learning or so forth, which is a harder problem.
Something that is a bit unclear to me is how much this pruning technique really is based on the discriminative nature of the task. So if you had a generative task, I'm not really sure that this type of throwing of the data would save. I feel that it's kind of like doing part of the work of optimization instead of confusing the model to go to a direction. You basically prune the data so that the model can go faster to a certain direction during optimization. Do you think that this technique would transfer to a generative task where you want to replicate a distribution, basically?
Yeah, we haven't, that's a really good question. We have not looked at data pruning for training generative models. We definitely haven't looked at that. I don't know. It's an open empirical question. You could imagine certain data fitting procedures on distributions that might not hurt the final input-output map of the generative model. So it's conceivable that it could work, but it's an empirical question whether it will or not.
Okay, let's thank Surya once again and go straight to the break. And we'll meet back here in about 15 minutes.